A matrix looks like four numbers trapped inside brackets. That picture is almost the least useful way to understand it. Instead, imagine the entire plane made of graph paper, with every point waiting for one instruction. Apply this matrix, and the whole grid shears at once. Straight lines remain straight, but space changes shape. The green and red arrows are special. They are the original horizontal and vertical directions. Once you know where those two arrows land, every other point in the plane is already determined. So a matrix is not really a table of numbers. It is a rule for moving space. Here is the trick that turns the symbols back into a picture. Read the first column as an arrow. For this matrix, the first column sends the horizontal basis direction to 2 steps right and 1 step up. Read the second column the same way. The vertical basis direction lands 1 step right and 2 steps up. Those 2 destination arrows are the control handles for the entire transformation. Any vector is just some amount of the first basis arrow plus some amount of the second. Linear transformations preserve that recipe, so knowing 2 columns tells you what happens to infinitely many points. Start with a unit square, 1 unit wide and 1 unit tall, sitting on the grid. Now apply a shear. The top of the plane slides sideways while the bottom stays anchored. The square becomes a parallelogram, but parallel grid lines stay parallel and no line bends. Something more surprising also survives. The parallelogram still has area exactly 1. That is what the determinant records here. This shear has determinant 1, even though the shape looks different. A matrix can radically change angles and still preserve area. Shape and area are separate pieces of information. Now use a matrix that really stretches space. Watch the same unit square and keep your eye on its area. As the grid moves, that little square becomes a much larger parallelogram and the readout climbs from 1 to 5. 5 is not special to that square. Every region in the plane gets 5 times as much area. A tiny circle, a triangle, or a complicated blob would all scale by exactly the same factor. For this 2 by 2 matrix, that factor is the determinant. 2 times 2.5, which is 5. That is the geometric meaning hiding inside the formula. The determinant is the plane's universal area multiplier. Now change the matrix so its 2 columns point in the same direction. The determinant becomes 0. Watch what 0 means geometrically. The square flattens, the grid collapses, and the entire plane becomes one line. 2 dimensions have been compressed into 1. Area is not merely smaller. Every transformed area is exactly 0. Here are 2 different input points. After the collapse, they land on the very same output point. If I only show you that output, there is no way to know which of those inputs produced it. The information is gone. That is why determinant 0 means the matrix cannot have an inverse. Compare that collapse with a matrix whose determinant is not 0. Nothing gets merged, so the move can be undone. Apply the matrix and the grid tilts and stretches into a new coordinate world. Now apply the inverse matrix. Every point travels back along the transformation and returns exactly where it started. The inverse is not a separate magic trick. It exists because the first move never destroyed information. In symbols, inverse times matrix equals the identity. On screen, that equation simply means the grid comes home. Invertibility is geometric. Did the transformation preserve enough information to rewind? There is one more structure the moving grid makes visible. Start several arrows in different directions. Under this matrix, most of those arrows turn as well as stretch. Their directions do not survive. But watch the yellow arrow on the diagonal. It gets 3 times longer without leaving its original line. That special direction is an eigenvector. The factor 3 is its eigenvalue. The equation says the same thing compactly. The matrix changes the vector's size, but not its direction. Eigenvectors matter because they reveal the directions a complicated transformation treats in the simplest possible way. Now the vocabulary fits into one picture instead of 5 disconnected definitions. A matrix tells space how to move, and the determinant tells how every area changes during that move. When the determinant is 0, a dimension collapses and information is permanently lost. When no information is lost, an inverse can rewind the transformation and bring the plane back home. Inside the same motion, eigenvectors are the rare directions that keep pointing along their own lines. Linear algebra is not really about tables of numbers. It is about what happens to space.